In this example, we're given the formula for a polynomial function, and we're asked to determine the zeros and then state the multiplicity of each zero. We're also asked then to state the degree of the function and determine the long-run behavior. So we'll start with the zeros, and what we're going to look at here, we know that a zero of a function is a value a, where f of a is equal to 0. So when we're looking at a polynomial function that's given in factored form, anytime we see a factor x minus a in that polynomial function, that's going to indicate that we have a 0 of a, coming from just the very basic principle that a minus a would equal 0. So looking at this first one, we have a number of factors there. We also have a constant factor. That's not going to affect whether there's a 0 or not. But let's see what our first one is. So first factor that contains a variable that we see is just x. And so keeping in mind that that could be written as x minus 0 in that really formal form, we have a 0 of 0. In other words, f of 0 equals 0 for this function. And when we look at the multiplicity, we're looking at how many times does that factor occur in this polynomial function. And for this factor, it's just going to be once. So that multiplicity will be 1. The next 0 that we're going to see is 7, and that's because we have the factor x minus 7 in there. And the exponent on x minus 7 in this case is a 2, which means that the multiplicity of the 0, 7 will be 2. And continuing, we have x plus 1 to the 5th. So what we're looking at there is what value of x would make that particular factor 0, and that value is -1. So -1 is a 0. And then again, looking at that multiplicity, we're just looking at the exponent there. That factor x plus 1 occurs 5 times. So we say then that the 0 of -1 has a multiplicity of 5. And looking at our last one, we have x plus 2, and similarly, that'll mean that we have a 0 of -2, and that exponent is 3, so we'd have a multiplicity of 3 there. All right, so we've determined all of the zeros of this function and their respective multiplicities. The other thing that we're asked to do with this problem is to state the degree of the function. And the longest way to do this would to physically be to multiply that entire expression out. But with this complicated a function, that would take quite a while. So there's a slightly different approach that we can take. And this approach is to look at the number of times that x appears in a factor of this polynomial. We know that when we have something like x minus 5 times x plus 6, we know that when we fully expand that, x squared is going to be the first term, and then we'll have all these things following. If we had x times x minus 5 times x plus 6, when we fully expanded that, we know that we'd have x cubed plus, and then a whole bunch of terms that followed. So when we're determining the degree of a polynomial, we're only concerned with the leading term. So all that we need to do is figure out what that leading term is, and we don't actually have to multiply this out to do that. So if we want to state that leading term, what we'll do is we'll look at how many times x occurs in a factor. So we have 1, 2, 3, and then we have another 5, which will be 8, and then another 3, which will be 11. So the leading term here is going to be 4x to the 11th. So we know that of all of those variable factors, x to the 11th will be the leading term, and then we just have that constant factor of 4. So what that means then is that our degree is 11. Now, as far as the long-run behavior, this is also related. The long-run behavior is determined by the leading term. And so when we're stating that long-run behavior, there's a couple different ways that we can state that. One is to say that this function will look like, so we could say it looks like y equals 4x to the 11th in the long run. Alternately, we could say something about what happens for really large values of x. So y equals 4x to the 11th is going to be an odd polynomial function, which will go like this. And so what we're really stating when we state that is that as x goes to infinity, we know that f of x will go to positive infinity. And as x goes to negative infinity, we know that f of x will go to negative infinity.